Hello everyone, I'm Li Yi. Today I will present my thesis, Custom Lifetime Value Prediction for Insurance, a comparative study of machine learning models. I chose this topic because my industry experience showed me how vital CLV is for business operations. My goal was to apply machine learning skills from my business analytics program to solve these real-world challenges. My presentation follows a systematic approach, covering everything from the abstract to final recommendations. Let's start with abstract. The insurtech landscape is shifting the industry from product-centric to customer-centric model. Predicting CLV accurately is key to optimizing resources. However, traditional models struggle with nonlinear data and long-tail distributions. My research aims to bridge this specific gap. This study follows the CRISP-DM framework, using over 9,000 records from an auto insurance dataset. I compared ridge regression with three ensemble models: random forest, GBDT, and light GBM. Results show that ensemble models clearly outperform traditional methods, with an R-squared of 0.677 and a 63% reduction in MAE. Finally, SHAP analysis reveals that policy counts that the greatest impact on CLV. Next, the background. The insurance industry is changing rapidly due to digital transformation. CLV is now essential for resource optimization, yet traditional linear models often oversimplify things and miss nonlinear relationships, while ensemble models can capture these complexities. They require SHAP to ensure better interpretability. Regarding the problem statement, although CLV is vital, current gaps exist. Linear models often fail due to right-scaled data. Meanwhile, black box models create two major issues. First, they pose GDPR compliance risks because they lack interpretability. Second, they suffer from poor attribution, which limits the effectiveness of strategies like bundling. This slide outlines my research objectives and the specific questions they address. My goals are to evaluate data patterns, compare predictive models, solve the black box problem, and propose actionable strategies. This leads to my core research questions, specifically identifying CLV distributions, comparing ensemble models against the ridge, and uncovering the key features that drive customer value. Now let's turn to the methodology. I chose CRISP-DM because it provides a systematic way to handle data mining. My process started with EDA, which reviewed specific patterns that guided my pre-processing. The dataset includes 9,134 records and 24 features. As we can see, CLV is heavily right-skewed and becomes multimodal after transformation. This highlights the heterogeneity that linear models often miss. For pre-processing, I apply a law transformation to stabilize the CLV distribution. I used one-hot encoding for categorical variables and Z-score normalization for continuous ones. I also designed a loss ratio variable to better capture risk. This entire process allows us to handle skewness and mixed data types for more robust modeling. In the modeling phase, I selected ridge regression as the baseline. To address the complexities of the data, I chose three ensemble models based on their distinct characteristics: random forest for its approach to variance reduction, GBDT for its iterative error correction, and LightGBM for its computational efficiency. I used an 80-20 holdout method to evaluate how each model generalizes while balancing accuracy and speed. To evaluate performance, I used RMSE, MAE, and R-squared. These metrics allow us to assess error sensitivity and variance explained. I also used sharp analysis to provide both global and local interpretability. Now for the findings. Regarding RQ1, the CLV distribution is red-skewed and multimodal. My analysis showed that dynamic features like monthly premiums dominate static ones like income, proving that behavior-based insights are critical. Regarding RQ2, ensemble models showed a clear advantage. Random forest achieved a much higher R-squared than ridge, with a substantial reduction in MAE. This proves that ensemble methods are far more effective. Moving to RQ3, the chart shows what drives CLV. Sharp analysis reveals that policy count and monthly premiums are the biggest drivers. Basically, more policies boost a customer's value, while compliance pull it down. Also, the dependence plot helps us identify customers for upselling. For RQ4, the waterfall analysis showed that customers with multiple policies bring in much higher value. The gains chart reveals that the top 20% of customers contribute to over 44% of total value. This supports our idea for better pricing and bundling. By using sharp insights, we can offer personalized service to high-value clients and enhance retention. Regarding impact, I propose CLV engine for dynamic pricing and using Sharp to identify high-risk customers. We should also focus on upgrading low-risk policies automatically. At the same time, we can provide exclusive services for top clients to maximize their value. In conclusion, while this study provides deep insights, it is limited by its reliance on static data, which warrants future research. Finally, I want to thank Dr. Hannah for her guidance, my professors and colleagues for their insights, and my family for their support. Thank you for your attention.